Hello and welcome to the video explaining differentiation behind a neural network. So, as we've seen previously, there's a forward pass and a backwards pass. So the forward pass, you get given input values, which I'm going to call x1, as well as weights, which I'm going to represent with w. So you've got x1, w1, so that'll be one input, this will be the weight for one, x2, w2, and B. So for this one, I'm going to assume that we've got two inputs, and so we need two weights to go to the next node. This all gets passed in, so we find a z value. So now the z value would be w1, x1, add w2, x2, add b. This will represent the z value. Now from this, we then find an a value representing the z value once it's undergone the activation function. So you can represent it as y hat or as a, which equals sigmoid for this one, because I'm using the sigmoid function. So that's sigmoid of z. So this is z, sigmoid of z. And now from this, you then calculate the loss function a with respect to y, where y is the desired output and a is the output of your neural network. The loss function is written as y take away 1, take away y, take away a. So this is the function for the loss, which I'm going to be using. Now, what we need to try and find is, because in the end we need to adjust these weight and bias values. So we want to find eventually is the derivative of the loss in accordance with the weight and the loss with the bias. So this is what we want to try and find in the end, so we know what to adjust the weight and biases by. So the first step to doing this is to find the derivative of the loss with respect to the activation. So dl over dA. Now to do this, we ignore the y's because we're only differentiating with respect to a. So then this will be y over a. And we're treating y as like a constant, so a singular value. So ln a differentiates to 1 over a, and then you multiply it by y because we're treating it as a constant. And then adding this to all of this differentiated, ending up with 1 take away y all over 1 take away a. Because 1 take away y once again is a constant, and ln of 1 minus a, the differential of that is 1 all over 1 minus a. So this will give you the differential of the loss with respect to the activation. The next thing we want to find is the derivative of the loss with respect to the z value, because what we want to do is we're kind of working our way backwards down here and then working our way backwards to here to adjust all of these. So next we need to find the derivative of the loss with respect to the z value, which using the chain rule is the same as derivative of the loss over, and then we can fill this in, but we know dl over dA, so we can do this. Now we already know this, but now we need to find the derivative of the activation with respect to the z value. So the activation function I'm using is the sigmoid function, which is written as 1 all over 1 plus e to the negative z, where z is this value that we've passed into the activation function. Now, so what we need to find is dA over dz, which using the quotient rule is 0 take away 1 and negative e to negative z all over 1 add e to the negative z all squared. This is due to the quotient rule, which says that the derivative of 1, which is 0, times by this value, which will just leave you with 0, minus derivative of this one, which will leave you minus e to the z, multiplied by 1 all over the bottom squared will leave you dA over dz. Now, with this one, we need to do some simplifying. So then we can simplify this down to e to the negative z all over 1 add e to the negative z, 1 add e to the negative z. Right. And then we can split this up into two fractions. 1 all over 1 add e to the negative z there, multiplied by e to the negative z all over 1 add e to the negative z. Now, let's turn over the page. So I'll rewrite this equation up here. We've got 1 all over 1 add e to the negative z multiplied by e to the negative z all over 1 add e to the negative z. There we go. So now we can split this up because we know that this eventually will simplify down to a 1 minus a. So we want to try and get down to this, where a, as is written here, is this 1 all over 1 add e to the negative z. So we've already got that there. Great. So that'll be the a. So now we just got to simplify this. To do this, we'll leave this as is, 1 all over 1 plus e to the negative z. We'll switch them all to a's later. All multiplied by 1. We can write this as e to the negative z add 1 minus 1. Because if you add 1 and minus 1, it changes nothing to the value overall. Add e to the negative z. Which can also be written as, I'm going to go this way, 1 all over 1 plus e to the negative z multiplied by, so we'll have 1 plus e to the negative z all over 1 plus e to the negative z. If we split this one into two fractions, minus 1 all over 1 plus e to the negative z. So this one will simplify down to 1, and these two will simplify down to a, leaving you with, as we've got here, a multiplied by 1 minus a. So great, this is the derivative of the activation with respect to dz. And now we can find the derivative of the loss with respect to z by multiplying the derivative of the loss with respect to the activation by the derivative of activation with respect to z. So we can do that here. dl over dz dl over dA multiplied by dA all over dz, which we know is minus y all over a, add 1 minus y all over minus a, so that's dl. This is multiplied to a 1 minus a. Now this we have to simplify out, which we got minus y. If we multiply both of these by a 1 minus a, minus 1,